So back to the physics. If there was a question about how does the g of k change when you go to Fourier space, and well, if you recall this problem from electrostatics, we solved the problem where you had one surface at y equal to 0 and one at y equal to a, which we held at v equals 0, both on the top and the bottom. And then we imposed some v naught of y on this wall here, which is at x equal to 0. And then the system goes on to infinity in this direction. Recall that we picked out, let's see, because of the boundary conditions, we found that only certain modes were allowed here, right? We had sine of kx, where k wasn't a wave number but some constant, which had to be so that the sine was 0 both here and here. And this is so this illustrates that you have to pick out the correct wave number, so to speak. While for the case we just solved on the blackboard, we had no restrictions on the wave numbers because there were no boundaries anywhere except at infinity, and then you can basically have any wave number. So I hope that illustrates that point a bit better. Also, one of the hard-working students in this class asked me about H parallel is equal to 0. We use this boundary condition in solving the fields in the waveguide. This is wrong, of course, because we have that above and below a surface. We have that H parallel in 1 minus H parallel in 2 is the surface current. And there's going to be some surface current. While the B1 normal minus B2 normal, that's continuous. So because the B is 0 inside the material, it has to be 0 right on the outside as well, just next to the interface. While this doesn't really tell us what is what's the boundary condition for, well, it doesn't connect H1 and H2 because we know that one of them is 0, but there's some unknown current which makes sure that this one is perhaps not 0. So this is the correct boundary condition. So if you want to work on those exercises, you should use that boundary condition and not this one, which I put on the blackboard. So sorry about that mistake. Okay. Now we're going to move on to the time-dependent equation with the Green's method. And now it gets a bit harder to find it gets a bit harder to solve the integral to get back to real space again. And the equation I'm interested in is, of course, the wave equation. Like this. Except now I have sources which depend on time. So this is the stuff we were discussing before we started this detour into Green's functions, this wave equation with sources for the potential. And the Green's function is defined in the same way as before. The D'Alemberian of g of r prime t prime is equal to delta of r minus r prime delta of t minus t prime. So there's one delta for each spatial dimension and one delta for the time dimension. And if we find the Green's function, well, then we know the solution to this wave equation here. We just integrate over the sources. Okay. Yeah, and you can easily show this by insertion. There was one thing I was going to say, but I forgot. Okay. Just as in the previous case anyway, we proceed by doing a Fourier expansion of this equation on the left-hand side, on the right-hand side, and see what we get out from that, see if we can solve the integral. So in principle we're doing exactly the same thing, except now we added the time dependence and the integral gets a bit more messy. So g on the left hand side is 1 over 2 pi Now there's a power 4 here. Integral of g of k and omega. Omega, that's the time frequencies, right? While k is the spatial frequencies. E to I k r minus r prime e to minus I omega t minus t prime d 3k d omega. Okay, now that's a big mess. Delta function of r minus r prime t minus t prime. That's just 1 over 2 pi power 4 integral over e to I k r minus r prime e to minus I omega t minus t prime d 3k d omega. And if anyone is wondering what is this spatial times time thing, well, it's a unit source, a unit charge, which is turned on in a short instant at at t equal t prime. So it's a unit charge which sort of pops into existence and goes back out, which is not physical, of course, but in the end we want to integrate over this. So the Green's function doesn't have to make much sense in itself, like the delta function doesn't make much sense in itself, but the integral over the Green's function makes sense. And yeah. Okay, and we insert this into equation 5 here. And we have the same as before, that the nabla square of the exponential just gives us k square. Equivalently, we have, let's see if I write that down. When I write the nabla r, it means with respect to the r system of coordinates. This is simply minus k square e to I k r. Similarly, dt square of e to minus I omega t minus t prime is equal to minus omega square e to minus I omega t minus t prime. Okay, this gives us the following algebraic equation for g. Let's see if I move this term here, the delta functions, on the left hand side, gather the integrals. I get that the integral looks like this. There's an integral sign and a bracket, k square minus omega square over c square multiplied by g of k omega. As before we got k square g of k, but now there's also the omega from the time dependence. And e to I k r minus r prime e to minus I omega t minus t prime d3k d omega is equal to 0 for all, let's see, r and t. And if this integral is to vanish always at all times, well then, well then this bracket will have to vanish. Okay, so this bracket vanishes, meaning that we find g of k omega. In principle, k vector, but there's spherical symmetry still, is equal to minus 1 over k square minus omega over c square. And the Green's function is hence, let's see, I can write the Green's function. I skip all the r primes, so on. You get the point. Minus 1 over 2 pi. Power 4. There's a d3k d omega k square minus omega over c square e to I k r e to minus I omega tau. R is equal to r minus r prime, and tau is equal to t minus t prime. Okay, so I found the Green's function if I can just solve this integral. Was there any questions on this?
Can you explain the way you got the c squared? And also you see missing minus 1 from the delta function.
So once again, there was a c squared somewhere?
C squared below the omega.
Here? Is there something wrong with it?
Just wondering if you could explain where you got it from.
Let's see. It's from the linear operator. So the D'Alemberian is di minus epsilon naught mu naught dt square. Okay, so this is c squared. So
You seem to be missing minus 1
from the delta function, let's see. Yeah, you're right. So if I write it as e to something here, minus 1, like this, happy? It should be plus 1, I guess, because there's a minus sign here. Well, in the end, that's going to be a prefactor. So you're right, there should be a sign somewhere, but it's either a plus or a minus in the answer, right? It's going to come outside the integral when we do the integral of the Green's function. So this sign isn't going to change, let's say, the shape of the solution, just this overall sign. So if you don't worry too much about that right now. What should I take out? Well. This part. Okay. So we were here. Yeah. So I just need to solve this integral, and then I know the Green's function, and then I have the solution for any source on closed form. Now, let's see, the omega integral is the extra part here. The k part is going to be easy, as long as we can solve the omega part. So first of all, let's look at this I omega, I call it. It's from minus infinity to infinity, e to minus I omega tau over k square minus omega square over c square d omega. There we go. Let's see. Yeah, that's basically the time dependence integral. So we solve that first, and then we're going to find that the rest of the integral is going to be the same as we did before for the Poisson equation. Okay, and now there's a problem because this is 0 at k is equal to, now let's see, ck is equal to plus minus omega or whatever. So we have two singularities on the real line, and we need to invoke some physical argument on how to treat these. So we treat the singularities with some physical argument in mind. And we'll see what that means. Yep. Now, note the following, that, let's see, this equation here. This gives us the potential for a unit charge which is turned on at t equal to t prime. So let's say that I turn on some charge here for a short amount of time. And then if I'm measuring the field over here, let's say, then I'm not going to see anything in, well, I'm going to have to wait at least a few nanoseconds because the speed of light is finite. So the fields that are created at that point takes time to reach me. Okay? So we require that for tau less than 0 or t less than t prime, then g must be 0. right? Because I'm integrating over g to get the potential, and the potential will have to be 0 before the fields can reach me, traveling at the speed of light. Okay? So this is going to be, well, the physical requirement on g, which is going to help us solve the integral. And I think this is a reasonable thing to require, because if you don't require this, then the potential occurring at some point in the future could affect the fields here now, as opposed to the fields here now being affected by a charge in the past. Just as we discussed before, the causality. Right. So I'm going to solve this integral, and I have to take care of these singularities somehow. So I take all of this out. See. Okay, and to solve this integral, we do a small detour into the complex plane. So now I'm going to draw a figure, which is the real axis here. We're integrating from -infinity to +infinity on the real axis, of course. But let's say that we stop at some finite point, and then do a detour into the complex plane. Call this contour gamma prime. And I could also go in the lower half plane, like this. So I call this contour gamma. So either I can integrate like this, or like this. And now you remember from complex analysis that the total curve integral is going to be the integral along this curve plus the integral along this curve. And that's going to be equal to the sum of the residues inside the contour. We're going to show that these arc integrals disappear, meaning that the residues will give us the integral directly. We had some singularities at, well, let's see, this is the omega axis, or real part of omega. Let's see, so at omega is equal to kc, and omega is equal to minus kc. There we have two singularities. I'm going to add a small epsilon to this, or subtract actually, like this. So the singularity is no longer on the real axis, it's slightly below for both of these. And the reason why it has to go down and not up will become apparent shortly. Okay, and we use the following trick, that omega is equal to x plus iy. So this is the real part of omega, and this is the imaginary part. So this is, let's say, x, and the y-axis in the complex plane. Now the integral looks like the following. I omega is equal to limit of epsilon goes to 0, because then I'm back where I started. From -infinity to infinity, e to minus I omega tau divided by k square minus, and now I added a small epsilon to get this off the real axis, so I don't have the problem with the singularity on the integration path. So it's omega plus I epsilon square over c square and d omega. Okay? So there's a pole at let's see, this is 0 at the pole, right? Meaning that omega is equal to plus minus kc minus I epsilon. And this minus sign is a minus sign instead of a plus sign from physical reasons. Let's see. Yep. Okay. Finally, note that e to minus I omega tau I write as e to minus I x plus I y tau, or e to minus I x tau e to y tau, like this. So this is the guy we're integrating over on the real axis, because then y is 0. And then when I go into the complex plane, I have to make sure to take the detour, which gives me an exponential decay here, because then this arc integral vanishes. So I need to go up or down depending on the sign of tau. So there are two cases to solve the integral for: tau less than 0 and tau greater than 0. So we start off by a tau less than 0. Then we integrate along, let's see, this was gamma prime, so I integrate along gamma prime. So I integrate along gamma prime, because then, let's see, e to, what was it, y tau goes to 0 as y goes to infinity. Okay? This term is going to, this factor is going to go to 0, ensuring that the upper arc integral is going to disappear, meaning that the curve integral is equal to I omega, the integral we're interested in solving, plus the integral along gamma prime. But this is 0, meaning that I'm left with just I omega. And this is proportional to the sum of the residues, which you know from complex analysis. Okay. Yeah, but there's no residues in the upper half plane. This sum is simply 0, meaning that I omega is equal to 0, no poles in the upper half plane. And this is exactly as it should be, because now g is equal to 0 for tau less than 0, meaning that I can't be affected now by what is going to happen in the future. So that's good for the sake of sanity. And in a second, we're going to see what happens for positive tau. Okay, so tau greater than 0. And now we integrate along gamma, because, well, the tau has changed signs. So this factor is going to go to 0 in the lower half. Yeah, in the lower half plane of the lower complex plane. So let's see, e to gamma tau, no, it's e to x plus I y tau, well, that's trivial anyway. It goes to 0 as you go down. Notes are a bit messy, sorry. So the curve integral is equal to I omega plus the integral along gamma. This guy here, make sure that it goes to 0 on the arc. So this term is 0. And we conclude that I omega is equal to the same value as the contour integral over gamma. No, sorry. It's on the closed contour, which is gamma plus the real axis. Okay, and that is minus 2 pi I and the sum of the residues. And there are two residues here. There is one here and one here. And we need to find out what those are. So we expand this by a delbrøksoppspalting, or partial fractions in English, I think. And you know how to do that, so I won't bore you with the details. But we find that EI omega is 2 pi speed of light k, and let's see, sine of k c tau. Meaning we only get a contribution when omega is equal to kc, essentially. And as epsilon went to 0, there's no contribution from the epsilon anymore, so we're happy with that. The rest of the integral, we essentially had that the complete integral, or let's see, g was I omega times I k, or actually I omega dk, because now we need to integrate the result over k. But that integral looks exactly the same as before. You have the k below here and so on. So it's the same as the Poisson equation integral. And finally, we find that the Green's function must be the following. It's minus the delta of t minus t prime minus r over c divided by 4 pi r. And as before, r is equal to r minus r prime, length of that vector. Yeah. Any questions? We found the Green's function for the wave equation now, so we can go back to the physics, unless there's any questions? No? Okay. Let's see, lecture notes. Okay, so a brief recap of what we did with the Green's function. First of all, we're interested in solving an inhomogeneous linear partial differential equation. So it's a linear inhomogeneous partial differential equation on the form L y of x. X could be in one dimension or several dimensions, doesn't matter. It's equal to some source term. And we wanted to solve these integrals for this, this partial differential equation for many different source terms. Or at least reduce the amount of work when we change the source. And then we start off by solving a different equation instead, which is the linear operator on g of x. X prime is equal to the delta function of x minus x prime. And we show that the solution is simply an integral. So y of x is any homogeneous solution, which the Green's function doesn't help us find, plus the integral over the sources dx prime g of x x prime s of x prime, meaning that the only difficulty left is finding the Green's function, and we know the solution to the equation. We find that often, but not always, a Fourier transform is going to help us. So we found G by Fourier transform. That is, we transformed the equation. We found an algebraic equation for G, solved the algebraic equation, and did the inverse transform to find the Green's function. And this is a neat trick in general. It's not just Green's functions. If you have a partial differential equation, you might want to try just Fourier transforming it, and then that might be much easier than solving it in real space. And finally, we just solve the integral for all the s's we want. So we solve the integral, and we're happy. And that concludes our detour into Green's functions. If there's no final comment or question. Okay. So we found the Green's function for the wave equation. Let's see. Yeah. We found the Green's function for the wave equation. Now we're going to show that the solution does indeed include the retarded time, and we're going to use the Green's function to show it. So, in the Lorentz gauge, the problem we want to solve is the following: that the wave operator on V is equal to the charge distribution. Now there's both space and time dependence, like this. And we know the Green's function for this equation, given the boundary conditions, that the potential should be 0 at infinity. So G is equal to, let's see, it's G of R, R prime, T, T prime technically. It's equal to minus delta of T minus T prime minus R over C, and then 4 pi R, and R is just the distance from the point I'm observing the potential to the point of the charge distribution. And now I can write down the solution. Because I know the Green's function, hence I know the solution, or I know a way to write down the solution at least. Let's see. In the form of an integral, and that is 1 over 4 pi epsilon naught integral over d3 r prime dt prime g of all that stuff, rho of r prime t over epsilon naught. And we can't in general solve the spatial part of the integral, but the time part of the integral is easy because that's just a delta function. Okay, so if I write out the Green's function, I get that potential is equal to, let's see, minus d3 r prime. By the way, this was wrong because the 4 pi is inside the Green's function and the epsilon is inside the rho. But it's going to show up in the answer. So first of all, the spatial, then the temporal integral over rho of r prime t prime, like this. And then there's a 4 pi epsilon naught r. That's essentially the Green's function. And the epsilon is from the source term. And then there's a delta function in the Green's function, t minus t prime minus r over c. Now note that there's only a contribution when t is equal to, well, when t prime is equal to t minus rc. So t is equal to, no, t prime is equal to t minus r over c. But this is exactly the retarded time, tr. Okay, so I just integrate over the time because it's just a delta function, it's easy. Meaning that v of r t is equal to 1 over 4 pi epsilon naught, and the integral, which turns out to be, oh happy day, the same as we found in our heuristic argument last week, rho of r prime t r over r. The time integral is gone. We see that the only contribution is from this retarded time. So not only does the potential take some time to travel here from the past, but the potential from this charge distribution depends only on what happened at the retarded time. Okay, and this is the same, as I said, as we found last week during our hand-waving argument, which was sort of approximative and so on. Now we use Green's functions, which turn out they gave us this retarded time thing directly from the formalism, so to speak. And this shows that retarded time is built into the equations. It's not something that we require of the equations. We don't sort of solve the equation and then say that the solution should be retarded because we know from physical reasons or blah, blah, blah. In fact, what happens is that the equations themselves know that, well, it's going to take some time for the news to get here. So the retarded time is built right into Maxwell's equations. And this was, of course, important for the derivation of the relativity theory. All this stuff with, for example, you can also measure epsilon naught and mu naught in a static experiment, right? As it turns out, that gives you the speed of light, which is kind of fascinating. These equations know the theory of relativity from before. You don't need to tell them to change like you need the Maxwell equations. So this is where Einstein got his inspiration, from the Maxwell equations. Okay, any questions on this? It was clear? Okay. We recall that the vector potential fulfills a similar equation component-wise. So the vector potential A fulfills the equation wave operator A vector is equal to minus mu naught J of R T. And now we see that each of these components fulfill the Poisson equation. So the Green's function is the same, the boundary conditions are the same. And finally, we can just write down the solution. Each component of A fulfills the same solution as for the potential. So A of R T is equal to mu naught over 4 pi integral over d3 r prime j of r prime tr, same as before, retarded time, over r. Okay? Because mathematically the two equations are exactly the same. I'm sure there must be someone who has questions about this, because it's not that easy.
When you perform the contour integral, you moved the singularities somewhat down from the line integral, whereas you could mathematically have integrated over the lines using a similar formula with sum of minus pi I residues or whatever.
Yep.
But then you would have gotten a, mind-bending, you would have gotten a contribution from the future if you did that.
Yeah, so there's a question that why did we put the singularities to the bottom or below the real line? And mathematically you could in fact have solutions like that, but then you would have advanced time solutions, meaning that the potential here now is going to depend on the charge distributions of the future. So we reject those solutions on on a physical ground. So I reject your reality and replace it with my own, which is more harmonic to the mind when you go to bed. Let's say, yeah. Anything else? Okay, I think that's enough for one Monday. So, see you on Wednesday.